Hey everybody, Mr. Waiter here, and today we're going to be going over waves and water and how the two are connected and how they interact. So to start, we need to know what a wave is. In physics, a wave is a disturbance or an oscillation, meaning a thing that goes back and forth repeatedly, and it travels through matter or space, and there's a transfer of energy that goes with it. For our purposes, a wave is a vibration that transfers energy through space. Now, obviously, the kind of space that we're talking about is going to be water, and we're talking about how this would make water waves. So we're talking about some sort of thing that causes a vibration that transfers energy through water. Like I said, vibrations make waves. When an object like a speaker vibrates, it creates a wave, and that would be a vibration in the air. And air is a fluid. A fluid is a liquid or a gas. And water is a liquid, just like air is a gas. So it operates the same way for both. You can't see it with air, but with water it's obvious. So if you take a look down there, you've got that wave machine. And if you've ever been to like lake compounds or somewhere like that, and you've been to one of the water parks, if you've ever wondered how they get those massive waves going through the pool, this is how they do it. There's a machine that pushes the water forward, and it makes a wave forwards and backwards. And because you're pushing water into the area where other water already is, it compresses it and makes it taller. This is called a compression wave. You'll see that later, but there's a bunch of different kinds of waves that we'll get to, but water does exactly the same thing as air. You can just see it, so it's easier for us to notice. Sound can make waves too, and since it's the transfer of energy, you can see it in liquids. So you can use sound to make waves. And I don't know what it is about this, but it's just really satisfying to watch. So the waves that are being made by the speaker match the frequency of the sound. So if you notice the lower frequency waves, lower frequency means bigger waves because there's less of them happening in the same amount of time. You'll notice that the lower frequency ones, there's a bigger gap, and the higher frequency ones are closer together. They're more frequent. And it matches with the tones that you're hearing too, so it's pretty cool that you can actually see that. So waves can make different shapes. You've got like, they're called square waves and sine waves, saw waves, and all those make different shapes. So as you watch it in the liquid here, you can even see that the liquid is making different shapes. Like that one is, if you freeze it, you can actually see that this one has like a different shape than this one. This one makes more of like a rounded peak shape, and this one looks like a perfect, like almost like an egg crate as it goes across, and it's irregularly shaped. So anyways, waves themselves are not a solid physical thing. Waves make physical things move. They're the transferring of energy, and the energy moves the physical thing. So when we're talking about waves in water, it's a little bit different because in physics, a wave isn't a thing itself, really. And in marine science, waves are the motion of the water. So people will look at the water and go, oh, look, a wave. What they're really telling you is, oh, look, the water is moving a certain way. So we just have to be careful about how we use that term in marine science. So you can see the same sort of pattern if you attach a water hose to a speaker, and you can actually see the wave that the speaker is making when you do that. So this is like obviously very slow-mo, but if you watch, you have that little hose is attached to the speaker there, and when the speaker vibrates, it's pushing the water, and it's moving at 25 hertz. Now there's a little bit of a camera trick going on here, but you can see the shape of the wave that the speaker is making. So if you froze that, you would see it's a sine wave, meaning it's making an up and down motion at a constant speed. And when they turn that knob on the machine there, what they're really doing is they're changing how fast the sound is moving up and down the speaker. Anyways, you get the idea. So the shape of water can be changed by sound. It can be changed by anything that's basically pushing energy through it. What you just saw there is basically how sonar works, which we'll talk about later on, but in a different video. But yeah. Okay, so how do we measure those waves? There are a couple of things that we care about when we are measuring waves themselves. In general, waves are measured by using terms that are called amplitude and wavelength. Amplitude is the height, wavelength is the length of a wave. In marine science, they use the term wave height because they're measuring actual waves of water. So it's the height of a wave. And that's measured from its starting point, which is also called the still water level, to the crest, which is the peak of a wave. So basically you're going to measure from this point here, where it starts, the still water level, up to its height. So in this case, the height is up to here, it's its crest. So this difference right here is the height of the wave. What you should notice is that it should be the same in the opposite direction too, and the bottom of a wave is called a trough. Also, that's the name of a thing that they feed pigs with, you know, like the big container that they put food in at a farm. Those are called troughs. That's where it gets its name from, by the way. Anyways, so you've got the troughs down here, and you've got the peaks up here. And if you notice, it's measuring the wave height from bottom to top here. The wave crest height is measured from the still water level up. So if you want to get the entire height from trough to crest, you would measure from the bottom of the trough to the top of a crest. And then wavelength is going to measure from a peak to the next peak. You could technically do it at any point in the wave, but usually it's peak to peak just because it's the easiest way of looking at it. You could also measure trough to trough, or you could measure it from like the still height to the still height. You'll get the same exact length every single time because every wave should be the same. They're consistent. One thing you may notice that's different between sound and the water here is that since water interacts with itself very strongly because it sticks to itself, it's polar, so it has this property where water sticks to itself. That's why if you put it in a graduated cylinder, it makes that meniscus shape, like the curved one. Water sticks to things. So when the water is moving in a wave, it will stick to itself as it's moving forward. And because of that, it causes the water to basically roll over itself, which is why you get those really cool wave shapes when you go surfing. The water gets pushed forward, and the rip curl is like the water is literally rolling over the rest of the wave. So you can actually see it. But that path that they're talking about in the picture on the right side here is because of the motion that it's making as it goes forward. Okay, so that's amplitude, wavelength, and the shape of waves. So what causes those waves in the first place? I know that there's obviously not a very massive wave machine in the water. As cool as that would be, the ocean isn't controlled by that. So just take a second and try and think about what kinds of things could make these waves happen in the first place. So there's a couple of different reasons, but the main reason is wind. You have air pushing over the surface of the ocean, and that causes water waves. If you have ever cooled off a coffee or something by blowing over the surface of the container, you have done this exact process. Now, you're not as powerful as the winds of our planet. Sorry, you're not the Coriolis effect, but you can do the exact same process and watch it happen. There's also a couple of other reasons. So you've got seismic waves and thermal waves, and there's actually more than just those, but these are the ones that are the most important for our class at least. Seismic waves would be caused by something underground, like seismic activity and tectonic plates and stuff like that. So if there's an earthquake and the earthquake occurs underwater, you'll notice that it pushes the water away. And on the little image on the left there of the video, GIF or GIF, whatever you want to call it, you can see that water rolling motion, like I referred to earlier, is happening here. And notice that the motion is larger at the top than it is at the bottom there, because since the wave is moving more at the top than the bottom, you're getting larger motion there, so you would get a larger change in where the water is moving to. And then on the right side here, we've got these currents, and you'll notice that there is a path that the water moves through. There's arrows basically dictating that path, and it can branch off in a couple of different directions. If you've ever watched the movie Finding Nemo, they actually refer to those. So you can actually track those currents, and this is the general pattern for those currents. Next, I just wanted to show you what the basic shapes of these waves are in the water. There are a bunch of different kinds. You don't have to know all the names and the types of waves. So I'm never going to ask you like, oh, what kind of wave is this? That's a P wave. I don't care. What matters is that you just understand that waves can make different shapes depending on like what happens to cause the wave at the beginning of it. So these are all demonstrations and animations from Purdue University. So I had to give them credit because this stuff is really cool. The research that went into measuring it and actually seeing this is really cool. So credit to them. But there are different types. The first one is a P wave, and that is a compression wave. So when you're talking about the waves in a theme park, you're talking about compression waves. You have something pushing straight forward, and that pushes the water into the water in front of it, and that's why you get the height change from those waves. If you look at the next one, this is called a shear wave. So if you had something that could push the water up and down and go forward to a degree, if you watch it at the very beginning right here, if you were able to pull the water up, which you obviously can't normally do, but if say you had an earthquake and the ground got shot upwards really quickly, you would make a shear wave. Shear means you're cutting through something. That's why it's called shears, because they shear through things. They cut through it that way. You can even see it though, right when the wave is moving, that it's an up and down motion as opposed to a forward and backward motion. Shear waves are also called S waves. Next you have Rayleigh waves. These are kind of funky because this would be more of like a rolling wave where something takes it and physically compresses it up and forward or down and forward, and because of that you get this rolling motion as it goes through. This is the kind of shape that you would expect out of something like slime, where it interacts with itself and it sticks together, so it's kind of resisting motion in one way as it moves forward. And at the end it makes note of the fact that you get that rolling motion towards the end there. And the last one is called a love wave, and I wish that wasn't the actual name, but it is the actual name. These are also referred to as L waves, and you get a side-to-side motion as it moves forward. So if you were to like take like a string or something and wave it, you are most likely making a love wave. You can make of that what you want, but you'd be moving it left to right and in a forward direction, so the wave would move forward. This is the same sort of motion that like a whip or any other object that starts a wave from one held point would do. So like if you took a jump rope, for example, or like a cord to a vacuum cleaner, and you held one end of it and you flicked it forward, this is basically what you're doing. Alright, so two general types of waves are transverse and longitudinal. Longitudinal means like a long, aligned shape, so front to back, like the compressional waves that we talked about. And then you have transverse waves, where they're moving up and down as opposed to forward and backwards. The confusing part here is that with water, you can make a longitudinal wave by compressing it like that wave machine, and it generates something that looks like a transverse wave. At the bottom I ask, where can you find these kinds of waves? In marine science, I think it's pretty obvious. You're going to find those waves in the water. You could also, if you could see the particles of air, you could also see that that's happening in the air as well. So, sound waves, since they're moving air, are a good way of showing this. And just so you get the idea, when you're pushing the air forwards and backwards, that's longitudinal, you get areas that are compressed, where there's lots of pressure, and you get areas where there's low pressure. They're called rarefactions. We care about the compressions, though, because that's where you're going to get the taller parts of the waves. The distance between those compressions is the same length as wavelength. So if you look from compression to compression, that's one wave. That would be the same as if you looked at the peaks and the waves that you saw earlier. So if this whole tube is 12 meters, what would the wavelength be? So try and figure that out really quick. Okay, so in order to do this, first you have to figure out how many waves there are. So if you go from compression to compression, that means you start over here on the left. So that's 1 wave, 2, 3, 4, 5. So if you had 12 meters, it would be 12 meters over 5 waves. So whatever 12 divided by 5 is. It might be easier if you did 10, because then you would have 10 divided by 5, which would give you 2. The point is, you can count the number of waves by going compression to compression. And then if you know the length of the object, you could actually calculate the wavelength. All right, last big idea is interference. So when you take 2 waves and they collide with each other, they are going to combine with each other and change the size of the wave. So you get 2 kinds of interference. You have constructive, like construction, you're building something. So that means you're building up the wave or making it bigger. And then you have destructive interference, which is when waves combine and they destroy, destructive, right? They're breaking down, so it makes it smaller. So you can see that if you take the 2 waves and you put them together, as long as they're synced up with each other, they're going to get bigger. That's constructive. If you do the opposite of that, this is how noise-canceling headphones work. You take the sound wave and you make the opposite of it, and your headphones basically generate the opposite sound on the outside of your headphones. Now you don't hear any sound on the outside. When it happens with water, it looks really, really weird because you'll have waves coming from 2 different directions, and if they crash into each other in a destructive way, it'll go from waves to flat. So, same idea here. If you were looking at particles of water or air, it's the same idea. The areas that are synced up like this, these 2 match up, so your result is a bigger wave. And if it's the opposite, meaning they are not synced up, notice how on the left here it's at the bottom, and on this one here it's at the top. When you put them together, it destroys the other wave. The 2, when they hit each other, just cancel.